Hi, in this video we'll introduce a family of continuous random variables called normal random variables. And the standard normal random variable that we studied in the previous section is just a special case of this family. Okay, so let me just recall that um, normal random variable the standard normal random variable, standard normal random variable z is a random variable with probability density function given by this formula fz is 1 over root 2 pi e to the power minus z squared over 2. Well, the formula you don't need to remember, but just at the moment you just need to see what is that. Then we learned also that the mean of z is 0. We just write numerical, and its standard deviation is equal to 1. So it has these two properties, yes, but everything comes from the fact that it has this PDF function. Well, we generalize this thing in general. Let me put this as a definition. If we start with a random variable, y with PDF. You see, the PDF of the normal random variable, it is a number times e to the power minus something squared over 2. But if it is general normal, we have f of y is equal to, there's a number here, so that number is 1 over sigma root 2 pi. Then e to the power minus, this is something squared over 2 times something. So that sigma comes here and y minus mu goes there. It's kind of similar to that, but with some work we did in the power of exponent. A random variable with that PDF is a normal random variable. So this is the definition, is a normal random variable with mean mu. So this number here that we subtracted from y is mean, and standard deviation sigma. So the sigma that you see here, that's the standard deviation. So what does this definition say is that for any mu, any number mu you give me, and any positive number standard deviation sigma you give me, we can define a new random variable called normal random variable with that mean and that sigma, which has this PDF. What you need to keep in mind is that, so first remark is that every normal random variable is fixed. So you have one normal random variable for any pair of numbers mu and sigma. So you give me any two number, mu and positive sigma, there is a normal random variable with that mean and that sigma. The second thing is that, remark 2 is that only when, only when mu is equal to 0 and sigma is equal to 1, we call it standard normal, or that's the only case we put the name standard, when mu is 0 and sigma is 1. Okay, how about the graph of the PDF? So compare the graph of PDF for normal random variables. Well, remember, for the standard one, the standard normal random variable z, what we have was, okay, so this is x-axis, this is y-axis. That was the bell shape graph, which was symmetric with respect to, which was symmetric with respect to y-axis. Now, in general, for normal, just normal random variable y, what happens is that in the general case, when you have a different mu, so if this is x-axis, this is y-axis, whatever the mu is, the symmetry of the graph will be at that point. So if this is mu, then we're still going to have a, we're still going to have bell-shaped graph, but the symmetry won't be anymore on y-axis. It will be at line x equal to mu. And if you consider different sigmas, so if this is the standard one, as you increase the sigma, the more spread out the graph will become. So it will be something like this. If the sigma is bigger, or if the sigma is smaller, it will be more concentrated around the symmetry. So for example, in this case, this can be sigma equal to half. For this guy, this can be sigma equal to 1, and for this one, sigma is equal to 2. So the bigger sigma is, the more spread out this bell-shaped graph will become. Okay, so that all being said, one thing that you may notice is that at the end of the table, at the end of the book, you only have table for standard normal random variable. How about the other normal random variables? So if you have a normal random variable with different mu and sigma, is there any way that you can find probabilities of event defined by those normal random variable? The answer to that question is in this mathematical fact, or maybe what people like to say theorem or proposition. And it says if y is a normal random variable with mean mu and standard deviation sigma, then there is a way to turn y into the standard normal random variable. How? It's enough to subtract mu from y and then divide it by sigma. So mu and sigma are two numbers. So y minus mu over sigma, you do that thing. If you do it, this is going to be the standard normal random variable. Or in other words, wherever you see this guy, take it out and replace it by z. This guy is equal to z. Well, this thing shows that how we can turn um, um, just normal random variable to standard normal random variable. How this is going to be useful? How is it useful? Well, the reason that it is useful is that now we can turn any event defined by y, any event defined by y, well, such as y less than b, can be turned into an event defined by z. How? So let us start with something like this. To be able to get to z, I need to subtract mu from y and divide it by sigma. So to be able to do that, let's subtract mu from both sides of this inequality. So this will be b minus mu. Then we need to divide both sides by sigma. So it will be y minus mu over sigma is less than b minus mu over sigma. You see that b was a number, mu was a number, sigma is a number, so we can, this will give us one number. Let me call it k. And also I know that y minus mu over sigma is the standard normal, so this is z. Basically, by doing those operations, subtract mu from both sides and then divide both sides by sigma, we turn y less than b to z less than k for some k. And well, if you have that, then you can turn, for example, probability of y less than b is going to be equal to probability of z less than k. And right away you see that why that fact is important. When someone asks you to find probability of normal random variable less than something, you do those operations, turn it to probability of z less than something, and then use the table to find the value. Let's just do an example, very quick one. Y is a normal random variable with mean 10 and standard deviation sigma. Then, for example, if I have probability of y less than 11, what I can do is that subtract both sides from, subtract mu here is 10 from both sides. Then divide both sides by sigma. Well, sigma here, let me put 2 here. Sorry. So we can do y minus 10 divided by 2 is less than 10. 11 minus 10 divided by 2. And now we know that this guy here is z. So I have probability of z less than, right hand side, as I explained before, these are numbers. 11 minus 1 divided by 2 is 1 over 2. In other words, probability of z less than y less than 11, for which we don't have any table, can be turned into probability of z less than 0.5, for which we have a table, and we can read that probability from the table, and that's the probability for y less than 11. In next videos, I will do more examples on this to show you how all works. But the important fact of this video, if you want to keep something in mind, is the fact I wrote in middle here. If you have normal random variable, you can turn it into standard normal by subtracting mean from y and dividing it by sigma. You will get the standard normal random variable.